record on this computer, and then I'm going to share. You see my screen?
Yeah.
Okay, good. Let me see where we stopped last time. Okay. All right. Okay, so to answer, just unmute yourself. And make sure that I can see you at all times. Don't turn off your camera. Now I can't see everybody because...
I have to grab something. I'm so sorry.
Okay. All right. All right. So who can give us some examples of protein analysis categories and applications? So we said protein analysis is not only quantification, right? What else? What do you remember from?
Purification.
Oh,
Go ahead, Jean.
Purification. Does it count?
Oh, yeah. Protein purification. It does count. Can you give me an application for it?
To make like isolate.
To make isolate ingredients. Yes, that's one application. What other application we isolate protein, produce and isolate for? Other than industrial scale production of an ingredient. Why do some of you isolate proteins?
so we can like analyze specifically the protein function, like without any other interference.
Yeah, so studying the structural and functional characteristics of the protein itself. That is good. All right, what other protein analysis category?
Protein characterization.
Protein characterization such as?
Like how we use HPLC to like characterize an identification. I think that should come together. But like how we identify using HPLC or to study a new ingredient, that would be the application.
So structural characterizations, looking at, for example, you say HPLC, we can say size exclusion chromatography to look at molecular weight distribution. We're going to talk a lot about characterization today. So protein analysis is not necessarily just quantification. It could be identification, it could be structural characterization, it could be functional, it could be all sorts of assays we do for proteins, not necessarily quantification. So can you list some quantification methods? Or one, or whatever. Caldol is one, our favorite, isn't it? What other protein? Dumas, the one we loved so much, and LICO is down. I just saw the email again. I saw the email and I told Noor I hate LICO. She said, who? So LICO is an instrument.
I also second that.
Yeah, oh my goodness. Okay. On what basis you would choose a method for protein quantification? Like if I want to go with the LICO versus BCA analysis.
Cost? For the Dumas is based on the nitrogen content.
Yeah, so LICO is the instrument. Dumas is based on nitrogen. That is true. Cost is very important too. It's like, what do we have available? Do we have the Caldol available? Do we have the nitrogen analyzer? We don't have either. But there's also another important consideration. If I want to use BCA, what does the sample?
If we have standards and it is non-reducing.
It has to be pure in BCA.
Yes, so both Charu and Priyanshi they are correct. So it has to be almost pure and in solution in order for us to use a BCA or Bradford or any other, or UV, for example, like a 280. It has to be a protein, mostly solution of protein, with minimal interfering substances, especially if we want to use BCA. Sharu was right. We shouldn't have high amount of any reducing contaminants other than the protein itself, because it's based on the reducing power of the peptides. So basically the method of choice has to deal with the cost of how quickly do we have 100 samples to run. We cannot do CalDAL. Basically, it's going to take us a long time to do it. So time, cost, the matrix of the sample, availability of the instrument, and so on. Okay, so we separate proteins, but on what basis we decide on which way is best to separate the protein?
Solubility.
Go ahead.
Yes, solubility based on the solubility.
Yes, Sarah, based on solubility of the protein. So are the proteins soluble in dilute salt concentration? Are we looking at globulins, for example, from plant? Are the proteins basically very basic proteins, so we need high alkalinity to solubilize them? So we are looking at the physical chemical characteristics of or the biochemistry of the protein. So basically what we know about its composition, is it high in basic amino acid? Is it very soluble in water? Is what temperature of denaturation? What's the isoelectric point of the protein? So what do we know about it? Is structure, its configuration, its chemistry that will allow us to decide on which way we can isolate it. And to isolate the protein, the first step is to kind of solubilize it and fractionate it from insolubles. That's kind of the first step. And then the purification step comes into play after that. Okay. Can you list some chromatographic methods to separate proteins?
Size exclusion.
Size exclusion, one of the most used for protein separation and characterization, helps us a lot in determining if we have soluble aggregates, if we have dimers, trimers, monomers, and also knowing the molecular weight of the protein. Very good. Other than
ion exchange method.
Ion exchange, can you give me an example of an ingredient I mentioned in class that is isolated via ion exchange?
Is it like whey protein isolated from casein using ion exchange?
Well, not isolated from casein. It's the way that comes out of cheese production to isolate it from whey. There's so many other components. Lactose, for example, is really high in whey. So they use ion exchange, and the company that used to do it with the patent, and almost the only company in the country, was Davisco, and now known as Agropore. I don't know if the patent is still protected, but it was the only company to produce it for the longest time. What other chromatography that Ali loves the most?
Yes, I was going to say hydrophobic interaction.
Yes, it is the hydrophobic interaction chromatography is used for proteins. It is made for proteins and it's used for proteins. So it is very common, and it's used to separate the protein from solubles like sugars or soluble oligosaccharides and such. So it's kind of a purification. It can also be used to separate different proteins within a matrix based on their hydrophobicity. Okay, cool. So we can do adsorption other than ion exchange. You can also use, for example, affinity chromatography. The word escaped me for a minute. And this is mostly used to separate particular proteins, like if we're looking at a particular antigen, or if we are isolating an antibody, or if we're isolating a specific enzyme. So it's a very, very specific way of isolating protein using chromatography. Give examples of protein separation. approaches based on difference in solubility. So can you give me an example we gave, or one of the examples we gave in class?
Salting out.
Yeah, we can salt out based on the charges of the protein and what we know about the protein charges. So if we have a mixture of proteins and they vary in net charge, you can use different salt concentrations solutions to separate them. Very good example. Okay, so these are kind of questions that might be embedded in your exam in different formats, but you need to know, you need to be able to give examples and differentiate between these methods. The next question that is grayed out, this is coming up in the next few slides, but can any of you give me a chemical assay that we use a lot in the lab for structural characterization?
DSC. Oh, sorry.
Anastasia, DSC, it is used for structural characterization, but is it a chemical assay or an instrument assay?
Oh, it's more of an instrument.
Yes. Okay.
Mhm.
A chemical-based assay, then thing that you need to add agents and do a lot of wet surface
SDS.
charge.
SSP.
SDS.
Okay.
SDS.
SDS gel, yes. So SDS gel is one. What else that you use a lot and you need to practice?
Surface
Surface
hydrophobicity.
surface hydro. That's very good. Another one that potentially Ali uses a lot too. What do you use,
OPA.
Alan? OPA. OPA to determine percent of free amine or blocked amine, or degree of hydrolysis as well. So yeah, so we'll go over some of the structural characterization. We divide them into chemical assay and instrument-based assay. Do you have any questions from last week's lecture before I move on? No, so you know the material really well, huh? Okay, I see two. Is there chat here?
It's Anastasia and I talking about the LECO, sorry.
Oh, the LECO. It's like, I hope it's not the dead soldier, just wounded.
Just a little wounded.
Oh, okay. So no questions. I guess what I'm gonna have you guys do is just start studying a little bit and gather some questions, because next week I'm gonna have a recorded lecture for you. I'll record it actually this Sunday, so you'll have it available for you all week next week. But then the week after would be an in-person lecture before spring break and before the midterm. So I would like you to come with questions that you want clarification on that will help you understand the material for the midterm. Okay, so if you don't have questions now, we are going to move on. One thing I just remembered talking about the midterm, there is another practice set, and it's based on protein separation characterization. So after today, you'll be able to answer that practice set. Also, it's 4+5. It's not mandatory, but it's recommended. You get extra credit and helps you study for the exam. And then there will be one more before the midterm, and it's practice set 3. Also, the topics are included in the midterm. So these two coming up, please try to work on them. But the third one is not ready yet because I haven't started that material. Okay. Good. Any questions, clarification about anything before I move on? No? Okay. So a lot of the assays that we're going to talk about next is looking at structural characteristics, and also looking at identification and characterization. So we're going to cover looking at amino acid composition and sequence. We're going to talk about molecular size, molecular interactions, surface properties. Functional properties will come up later, not covered here. And then we're going to talk about denaturation and molecular configuration. We're going to talk about ways to determine secondary structure, for example, and some tertiary structure characteristics as well. So we're going to talk about a lot of different methods that can be used for the same type of characterization. For example, amino acid sequence can be done using mass spec, MALDI, we call it ladder sequencing, using MALDI, and then also N-terminal sequencing is another form of determining amino acid sequence. Molecular size, we're going to talk about gel electrophoresis and size exclusion, two different forms that will give us molecular size distribution, or we call it protein profiling in other cases. We're going to look at the denaturation state. There's so many different methods that are used to determine the denaturation state, and then the secondary structure and some tertiary structure characteristics. So there are so many different methods, and I like to categorize these methods as chemical versus instrument-based method. So the first one that looks at molecular distribution, polymerization, aggregation, most of you are familiar with, which is gel electrophoresis. So in gel electrophoresis, you can either do a one-dimensional or two-dimensional, and I'll give you examples of when we use either. And also it gives you an idea of some form of molecular interactions. So in STS page, many of you are familiar, we run it without BME and with BME, for example. And when you run it with BME, it's going to reduce disulfide linkages. So if there are disulfide linkages involved in the quaternary structure of the protein or involved in large aggregates that we have in the protein, they will be broken, and then you can see the different components. So that's why it can give you a little bit of some molecular interaction information. So there are three forms of gel electrophoresis, or what we call them polyacrylamide gel electrophoresis. You know it as PAGE, but how many of you knew that it was, PAGE stands for polyacrylamide gel electrophoresis? Or who didn't know? And it's okay not to know. Anastasia?
Yeah.
Who else? I'm gonna see who's gonna. Yeah, Saj, great. I love it. Just tell me, who knew then? Just say that I knew it. Priyanshi knew it. Madhvi knew it. Okay, I'm not seeing everybody else. Let me make it bigger, so I don't know if anybody raising their hand. I just want to make it as interactive as possible over Zoom, which is really hard. Okay, so that's not boring too. Coleman, did you know? Or you didn't know? You knew. Okay. Polyacrylamide gel electrophoresis. Normally in class, I bring a gel with me, and I would open the gel and I would hold it with bare hands without gloves. Am I crazy to do that? Or is it safe to hold the gel? Yi, what do you think? It's not safe? Is it safe or not safe? Yi says not safe. Who agrees that it's not safe? Raise your hand so I can see you. So Pam is crazy? You know acrylamide causes cancer. Pam already has cancer. No, just kidding.
Damn.
That's not the reason I hold the gel in my hand. Okay, so why would I hold it? Because acrylamide, when it's in powder form or liquid form, is carcinogenic. When acrylamide forms a gel, then it's no longer carcinogenic. You can hold the actual gel in your hand and not worry about it. So it's polyacrylamide because the acrylamide form polymers actually. So the acrylamide polymerizes and then forms kind of a matrix with the specific pore sizes. The higher the percentage of acrylamide, the smaller are the pore size. So if you, depending on the size of the proteins that you want to separate, you can decide on the percentage of acrylamide. So usually for peptides, we use above 18% acrylamide. If we have a mixture of proteins that vary in their molecular weight, we usually use what we call gradient gels. And most of you use in the lab gradient gels. Either, I don't remember what it is, 4 to 20% maybe is the common one we use in the lab. And that allows you to separate proteins of different molecular weights, so that the large gels can be, the large proteins can also be moved down the gel. If we use a very high percent acrylamide and there is no gradient, most of our large molecular weight proteins will be right on the surface, on the top of the gel, and won't move downward. So for our purposes, we tend to use the polyacrylamide gel that is gradient gel, that has large to small molecular weight, not molecular weight cut up, or pore sizes, I would call them. If I'm constantly using whey protein, for example, and whey protein is mostly small molecular weight. You have the alpha-lactalbumin and beta-lactoglobulin. They are 14 and 18 kilodalton. You can use like a 14% to 15% polyacrylamide gel, and that would be just fine. But because our proteins range, especially subunits, can range from 10 kilodalton and up to 100 and above kilodalton, we'd rather use the gradient gel. Any questions there? Okay. Let's see, I'm going to make this small again. Urea gel, this form of gel is used a lot for specific type of protein. For example, when I was a postdoc at Purdue, I used urea gel a lot because I was looking at casein proteins. And caseins, you know, you have 4 different caseins, and if you want to separate them on a gel, you cannot use SDS page because they have very close molecular weight. They won't be separated. So urea gel separates based on charge to size ratio. So you will have them separate based on their net charge as well as their size. In SDS page, they separate based on size alone. Do you know why and how? What does the SDS do? All of you run, most of you at least, run SDS page. Do you know how the proteins separate? On what basis? And what does the SDS do? Anybody?
Are you asking how it travels down the gel?
Well, what does the SDS do to the protein? So
It breaks.
It
So
breaks it down essentially as it moves through it.
What does
right?
it do?
Doesn't it slightly like denature and break down the protein?
It does denature, it breaks non-covalent bonds, definitely. But what it does to the protein, you know how it moves? You run a voltage, right? So they're all moving down. But we know that the proteins have different charges. They're not all net negative charge, they're not all positive charge, they vary. But all the proteins, when you run them on SDS page, they go down. They go from negative to positive. So what that means, your SDS is interacting with the protein and giving a net negative charge to all of your proteins. So they're all negative, they're all denatured, all negative, and they all go down the gel in one direction. So they separate only on size, based on size. Okay, now,
So, Pam, sorry, if the SDS didn't alter the charge, then they wouldn't all be able to travel down the gel like they do?
No, because they won't be all net negatively charged. And in electrophoresis, you have your electrodes, the negative and the positive, and you're running the gel, so all the electrons or negatively charged are going to the positive electrode. So they have to all go, when you run the voltage, they have to all move down. And if the protein is not negatively charged, they're not going to all go in one direction down. They will stop, like in urea. Urea denatures the protein but does not impart a negative charge. So they separate based on how they are charged at a particular pH and also based on their size.
And how exactly does SDS give a negative charge to all of them?
Because SDS is detergent that carries a negative charge and it interacts with your protein.
Excuse me.
Yeah.
When different amino acids have different charge, maybe one can be highly positive, another one may be less positive. Who will migrate faster, will migrate slowly?
So when you have SDS, all your proteins will be negatively charged when they interact with SDS. So all of them will carry the same net negative charge, and that's why they all migrate at the same time together, and they separate based on their size, based on the pores of the gel. Okay. So the SDS detergent makes them all negatively charged. Okay, good. All right. So now the last one is the native page, and this is not very commonly used. Basically, you're not adding any detergent or any denaturing agent, and it doesn't give you a lot of information because the proteins, especially, they differ in charge, they differ in size, they some of them are in quaternary structures, they won't separate, they won't move down if they're so large, like soy protein, for example, over 300 kilodalton is your glycinin, for example. So if you don't have a denaturing agent that breaks non-covalent interactions, then the proteins won't migrate. So the native page is very, very specific for specific proteins that will potentially go through and migrate, but it's not commonly used. I haven't encountered in our protein field any paper that use just native page, but it exists native because you don't add any detergent or any agent that will denature the protein. Okay, so, and I normally bring to class all of these different tools, but you mostly all know how to run a gel, but now you would get your gel in a cassette, a plastic cassette, already with wells pre-made. In the past, we had to make our own gels and pour them in a glass make that we made them handmade into a cassette. So it used to take the whole day to prepare a gel and run a gel. Anyway, but now you buy them and they come in different acrylamide concentrations, and you would take, you would put your cassette in the compartment. What do you call that? I forgot. What do you call this chamber? This buffer chamber?
I just call it a chamber. I don't know what
I thought it had a name. I forgot. But anyway, so there's a chamber where you put your cassettes and then you pour your running buffer. There's a specific running buffer that you would use, and then you remove the cassette. But you have to wear gloves when you remove the cassette. Otherwise, proteins from your fingers will go into the wells, and then you will have phantom finger proteins that will show up in your gel. So we always wear gloves obviously, and then you remove that cassette, and then in each well, you will inject a known volume with a known concentration of the protein. And then you would attach the, you put the covers on that has the wires that go into a voltage generator, and then you run the gel, and usually your proteins are put in, we call it Lemley buffer, so it has a blue color, so you would see them going down the gel. But the proteins are not yet stained, so you would see the front, the sample front going down the gel, and when it reaches just above the end of the gel, you turn it off, and then you would want to break the gel, remove the cassette, remove the gel very carefully, and then you stain it in Kumasi blue stain. And then you destain the gel after that. You have to destain, otherwise your whole gel is blue. But when you destain, and a destaining, either there used to be a specific destain solution that I would use. I think you guys now just use water to destain. I used to use acetic acid with some alcohol to destain. It was shorter period of time to destain, but then the gel shrinks a little bit. Because it looks funny after that. Anyway, now you just destain with water, and then your protein bands will show up because the Kumasi blue will bind to the protein, I believe, via hydrophobic interactions. And then you can see your protein bands, different subunits. You run a marker, a molecular weight marker, so you can estimate the molecular weight of your bands. We use the gel electrophoresis to look at different protein bands, to look at polymerization once we use BME, which is the reducing agent. We also, for example, in this case, we look at hydrolysis of the protein by different enzymes. We will see that some enzymes target one type of protein versus another enzyme targeting another set of proteins, for example. So SDS page has a lot of application looking at hydrolysis, specificity of hydrolysis, polymerization, the range of molecular weight of your protein, and the mixture of your protein, the profile of the proteins in your mixture or in your sample. So lots of application, very useful. It kind of helps you see the impact of processing. If you're trying to polymerize the protein by enzyme, you can see if your enzyme worked and you polymerize the protein. If you're trying to see the impact of the thermal treatment or impact of your extraction with high alkalinity, how it impacted your protein. If you want to look at, if you did salt extraction, you want to see what proteins are extracted versus using water versus using alkaline. So it's really very helpful to give you kind of an overview of your protein mixture.
Pam, I had a question.
Yeah.
So when I'm doing glycoprotein staining, does that utilize the SDS page? Or what? That is SDS page?
It's SDS page, but it's different than Kumasi blue. It will stain the proteins that are glycated pink. So then when you run your gel, if you see pink banding or smearing, you know that these are glycated protein. So it's a specific type of stain that would bind to a glycated protein.
Okay, so it's just the stain that's different.
Yeah,
okay.
The stain is different, but it's the same gel. Yeah.
Thank you.
Yeah.
I have one question as well.
Yeah.
So some bands are thicker than the others. So what does a thicker band mean?
Thicker bands? Okay.
Yeah.
So the thicker, whoops, I went far ahead. Yeah. So you load based on protein content, right? So if some protein bands will be thicker than others, that means you have higher proportion of that particular subunit than another subunit within that same protein. So let's say you prepared 1 milligram per milliliter protein. In that 1 milligram, let's say you have 60% beta-conglycinin and 20% glycinin. So you'll see the beta-conglycinin bands darker than the glycinin bands. But in each lane, you have total the same amount of protein. That's why it's very essential to load the same amount of protein. So you can, if you want to compare different samples, you would know that this variety, for example, or this sample has more of this subunit than the other. So the thickness of the band is due to the concentration of the protein. So the more of that particular protein is present, the thicker is the band. Does that answer your question?
And
Yeah.
I have a quick question. Basically, once we use STS page specific for the plant proteins, we are able to separate the mostly albumins and globulins. But what about the prolamins and glutenins for instance, cereal proteins?
So
Can we
usually when you run cereal proteins for prolamins are usually not disulfide linked, and they are, you can see the prolamins just run through the gel and you can see the prolamins band. The glutenins, like glutenins, for example, if you don't run under reducing conditions, they will be all at the top of the gel. So they're large molecular weight mostly. So you would really need to use a reducing agent so that they migrate through the gel and you see them. So when we're running gluten, extracted gluten, you really have to use a reducing agent in order to see all the components of the gluten, extracted gluten. And here, this next example, you know, if you run soy protein under non-reducing conditions, you will see that you have your legumin or the glycinin. You would see it at around, what, 60 to 70 kD, but then when you reduce it, then you see your acidic and the basic subunits separated, which you won't be able to see it without the reducing agent. And also without the reducing agent, if it is like, as you know, a commercial concentrate or an isolate, most of them will be aggregated and smeared like that. So you won't be able to see your individual bands unless you reduce in order to see the individual bands. In size exclusion, for example, you're able to see the protein in its native form if it's not aggregated, because then you run in buffer without SDS. And then you add the SDS, you solubilize some of those insoluble aggregates, you might see soluble aggregates, and you might see the functional proteins. With size exclusion, you get better idea about the molecular distribution than just SDS page, because SDS page, you have the SDS and it's denaturing. So you break non-covalent interactions. Yeah, so here basically some proteins are in quaternary structure like soy. So we will learn when we cover legumes and oil seeds that those types of proteins, especially the one of the globulins, they associate as hexamers. And within the hexamer, we have a monomer that is actually a polypeptide that is linked by disulfide linkages. In order to see the subunits of this monomer, we have to break the disulfide linkages. And having a reducing agent like beta-mercaptoethanol or DTT helps you break those into their original subunits, and then you can see them down the gel. So this is the subunits of this one monomer that is linked by this red bond, which is the disulfide linkage, basically.
So the SDS breaks the non-covalent bonds, and then the reducing agent breaks the disulfide bonds.
Yes. If you have bonds that are formed via a different type of covalent interaction, you won't be able to break it. So if you have Maillard-induced polymerization of the protein, you would see them as polymers, no matter if you add a reducing agent or not, you won't be able to break that type of covalent interaction. You will only with the reducing agent be able to break disulfide linkages. And SDS breaks hydrophobic, hydrogen bonding, ionic interactions. So it is basically, if you have your hexamer, in this case, this black line is hydrophobic interaction, dotted lines are mostly hydrogen bonding and ionic. So you can break that hexamer into its monomers, but if you want to see the subunits, you have to use a reducing agent. Okay, any other questions? They're all good questions. I like that you guys are asking, because many of you just do the method and not really know the concept behind it, and that's why you're in this class. So it's good. It's okay to ask. It actually would be much appreciated to ask.
Pam, I have another question, and I don't know if this is too complex right now, but sometimes, especially in Nigel's work, you guys talk about dimers on SDS page.
Yeah.
What is a dimer and how do you identify it on the gel?
Yes, so if you know the monomer molecular weight, let's say we know that his particular globulin has around 50 kD, and the globulins in oats, in his protein, they can form disulfide linkages with each other because they have sulfidyl groups that initiate disulfide interchange. So depending on the extraction conditions, the processing, any heat treatment, a monomer of a globulin can actually bind via a disulfide linkage to another monomer, and it will migrate to 100 kD. And you would go, okay, so 100 kD is about double the 50 kD, so we think that's a dimer. Yeah. Again, these methods are qualitative, and there's no like 100% certainty. So if we want to really know that these are dimers of the same monomer, you want to do proteomics work on them. You want to take that separated dimer from the gel, break it down, hydrolyze it, run it on LC-MS, and then determine the identity of the peptides. So yeah, for confirmation, you have to do more than just observation on the gel. Okay, very good. Okay. Now, 2D gels, we use them quite a bit for different purposes. 2D gel, usually we use isoelectric focusing coupled with SDS page. So in isoelectric focusing, we are separating the protein based on charge, not on size. So here, what you do, you also get an acrylamide gel, and we call it a strip, in this case, a longitudinal strip made up of acrylamide, all similar pore size, not a gradient or anything, so because we're not separating based on size. And then what you load on that strip is a mixture of large or relatively not so large molecules, but molecules that carry a lot of charge on them, that have multiple charge units on them. And then you run a voltage. So these molecules are going to migrate. So we call these amphilites. It's written here. I forgot that I've had it here. So amphilites. So these amphilites, when you run a voltage, they are going to migrate based on their charge, positive or negative, and they will be focused in a certain region along the strip. And usually the strip goes from pH 3 to pH 10. So those that are very positively charged will be around the pH 10 region, and those that are negatively charged will be around the pH 3 region. Okay. So now you created kind of a gradient, a pH gradient on your strip. Then you would load your sample on that strip and run voltage again. So your proteins now will migrate and will stop at their isoelectric point. Wherever there is the ampholyte that is equivalent to the isoelectric point, the protein will stop migrating and will stop there. So they are focused. So isoelectric, hence the name isoelectric focusing. So the protein will stop there. And if you develop the strip by, putting it in Kumasi, then you'll see different bands of the protein, and you'll know that they are separated based on their isoelectric point. But this is not enough in the protein world, because proteins not only differ in charge, they differ in size. So sometimes you might have multiple proteins that have the same charge, and sometimes you will have multiple proteins that have the same size but different charge. So if I want to enhance the separation of my proteins, I would use 2D gel electrophoresis, where I would run my strip first, and then I would get an STS phage gel, similar to the gel you get, but instead of having multiple wells, like you have 18 wells or 24 wells or 12 wells, depending on the size of your gel, you will have one long well. So basically longitudinal to the width of your gel, with one place to put the molecular weight marker, one well to put the molecular weight marker, and then a longitudinal space where you slide down your strip that you have already run. So before staining, so you take that strip that you've already run on electrofocusing, you put it in your SDS or Urea denaturing agent to denature those proteins. And because if you put it in SDS, they will all be now negatively charged, and they will migrate based on size, like SDS, regular SDS phage. So you take that strip that you put it in your buffer or SDS solution, and you put it in place on that bigger gel, and then you run your electrophoresis like normal. And then you will have your proteins now separated, first dimension on isoelectric point, second dimension on size, and you will have something like this. So here you have what you can see here, two different proteins that have different charge or isoelectric point. They migrate to the same molecular weight. So if you ran a gel without the separation, those two proteins won't have been separated. They're two separate proteins, but they migrated to the same molecular weight. Here, if you run only the isoelectric focusing, you might have a couple of proteins that have the same charge or isoelectric point, but migrated to two different places on your gel. So similar charge, different molecular weight. So with 2D electrophoresis, you have a stronger separation, more powerful separation of your proteins. Now, this is an example where we use 2D electrophoresis. So here we were looking at immunoreactivity of soy protein. And we separated soy protein isolate on the first dimension. And we took that soy protein and separated it on first dimension with isoelectric focusing, and then size. And then this is one sample only. So this one, SPI, here we see it all here. You see many more dots separated. You see all of these 4, 5, 6 different proteins all having the same molecular weight, but they're actually different subunits or different polymers of the protein. So why is that important? Why did we do that? At that time, we wanted to see which of these proteins is immunoreactive. So if I run an immunoassay on this, I won't be able to determine which of the proteins is immunoreactive. But here I have 1, 2, 3, 4, 5, potentially 6 different proteins. Then I would be able to see if this is immunoreactive or this one is immunoreactive or what have you. So you get the gist of it is I get better separation so that I can visualize better my protein. And if I'm running a particular assay that requires a better separation, then this would be a place to go. This is another characterization work we've done with camelina protein. So you run your camelina protein on a gel, and then you see all of these different banding, 1, 2, 3, 4, 5, 6, 7, potentially. But when I take this one protein isolate that I run on one of these lanes, and I run the sample on a 2D gel, then I'm able to see the different variants of cruciferin, the different variants of beta, the basic cruciferin and the acidic cruciferin. I'm able to see the napin separated into multiple subunits as well. This helped me characterize a little bit better the camelina since it's a new protein that we're studying. So this showed me that most of these proteins are really basic proteins, mostly around their isoelectric point is in the basic region. So that explains what camelina, for example, you need really high alkalinity to extract that protein. So it is mostly basic protein. It won't solubilize at neutral pH. If you just put it at water or pH 7 or 7.5 like we do for soy, you won't get the protein out. So this tells me why. This tells me that, oh, okay, it's mostly basic protein based on this 2-dimensional gel. Is it time for a break? Go ahead, question.
I had one question, Pam, about the previous slide, actually. When you did the back-to-back gels with the, I think you said isoelectric gel, and then you did the amino assay. Are you taking your sample from the isoelectric gel and then running it back through the amino assay, or how are you?
Yes. Yeah,
Okay.
that's gonna come later in the lecture when I show immunoacids. But just to answer your question, not to leave you dry. So first we use this strip to separate based on isoelectric point. Then we put this strip on top of this gel that you see here on the right. I don't know if you can see my mouse here. We put it on the top. And then this is the regular SDS page gel. And then you put that strip on the top and the protein will now migrate based on their difference in size. You take this gel and you transfer the gel into a PVDF membrane. So you blot it. So all the proteins bands are going to be blotted onto a PVDF membrane, and then you incubate it in your antibodies with the antibodies. And the antibodies would react with whatever protein is immunoreactive. Yeah, we will explain more the process later, but yeah. And that step I didn't show here. It's just showing that this separates it more for that type of assay that comes later. Good. Any other questions here? All right. So I will stop here for 5 minutes or 7 minutes until, I was going to say 11, but no, until 4 your time.
Hmm.
Okay. Let's come back. Waiting for everybody. Okay, I think most of you are back, so we can continue. All right, so that took a little bit to cover the SES page, but I think it was good to go over that. Now, next we have a few other assays that tells us a little bit about the structure of the protein. So the surface hydrophobicity assay, it's basically a wet chemistry type of assay where we look at the surface of the protein in terms of its hydrophobicity. So we use a reagent, ANS, and that reagent binds via hydrophobic interactions with the hydrophobic surface of the protein, and it fluoresces. So it's based on measuring the fluorescence. So the more hydrophobic residues are on the surface, the more ANS will bind and more fluorescence you will get. So you measure kind of a fluorescence index in this type of assay. So first of all, it tells you for native protein that did not undergo any potential processing, it tells you it is original surface hydrophobicity. And then it tells you after that, if you process, if the protein denatures, then the proteins unfolds and the hydrophobic residues that were hiding from aqueous in the interior of the protein are more exposed now, and then your surface hydrophobicity will increase. So if you heat like for longer time at a particular temperature above the denaturation point, you will gradually unfold the protein until you reach a maximum point. So since there's no board behind me right now to show you, but you want to imagine that we draw a two-dimensional graph with the y-axis and the x-axis. And let's say on the y-axis is your surface hydrophobicity index. And you go, let's say, you start, let's say, at 500 at time 0 of heat treatment. And when you start gradually heating and increasing the time, the protein gradually unfolds. We call this partial denaturation until you get to full denaturation. And then your surface hydrophobicity index will increase, and then it reaches a maximum. And then at the maximum, it's like a hill. It starts decreasing again with more heat time or increasing the heat temperature. So with more aggressive thermal treatments, the protein, suddenly you're going to have a surface hydrophobicity measurement that is decreasing. So it's the bell shape. You start at a certain point, you increase, you get to a maximum, and then you decrease. What do you think happens when we see a decrease? Does the protein folds back on itself and your surface hydrophobicity goes back to normal, or what do you think happens? Why do we have this decrease after you reach a maximum? One would theoretically think that, okay, I reached a maximum, the protein cannot unfold anymore, then it should plateau and just stay at the top, no matter what we do. But in fact, it doesn't plateau, it decreases.
Is it related to the free energy and entropy concept we read earlier? Like, because we are giving heat, the protein is still like in a chaos, and finally when like it reaches a point where it reassembles itself, that's where the surface hydrophobicity keeps decreasing.
So it does reassemble itself, but it doesn't go back to where it was originally. What happens when you have multiple proteins in solution, molecules, all unfolded now, and the hydrophobic groups are exposed, and you have water around you, what would the proteins do?
So they are going to they are going to interact each other to create the
Exactly, they're going to form polymers and aggregates, because now you have that much hydrophobicity on the surface. They don't like the water. They're going to be attracted to each other, and heat actually enhances hydrophobic interactions. So now they're going to come together and they're going to form polymers with each other. Now the ANS will not find those hydrophobic regions anymore, or it will find less of them, then the surface hydrophobicity will decrease. So when we measure surface hydrophobicity at any time point of that protein, if we get a protein ingredient and we measure its surface hydrophobicity, it doesn't mean that it is, you know, not in a native form if the measurement is low. We don't know. That's why it's not a standalone method for determining the protein structural characteristics. So usually you run it along with other things. You run a gel, you run surface hydrophobicity, and the gel tells you, oh, there's a lot of polymers. So that protein, and then you run DSC and you see that there is no peak. So in your thermogram, no endothermic peak. So you go, okay, so protein is denatured. However, because it's polymerized, the surface hydrophobicity is not as high as we expected it to be. So it's a good method to follow if you are looking at a native protein and you want to determine the impact of heat-time combination on the structure of that protein. You can do surface hydrophobicity as a standalone measurement. But if you're working with so many unknowns and you're not sure what to expect of this protein structure, you really have to measure surface hydrophobicity along with other structural characterization. But it's an important measurement to make, basically.
Pam, just to confirm before you move on, so ANS binds via hydrophobic reactions. So the more hydrophobic your protein is, the more ANS will bind, so the higher surface hydrophobicity.
Yeah, and the higher fluorescence, you will get a higher fluorescence index. Yeah.
Pam, I have a question. So when we run this assay, we have to do it fast. Is it because it's light sensitive?
Oh, you have to do it fast? Like
you have to add your ANS very quick and then cover it with foil before your 15 minutes.
Yeah, because it's based on measuring fluorescence. And if you lose the fluorescence, the light's emitted, and then you would lose the sensitivity of the method. Because it's based on emission of light. Yeah. Good. What else?
Stressful.
Huh?
I said it is stressful.
That and the emulsification stability assay. Okay, so moving on to surface charge, and usually surface charge can be measured by chemical assays, but often in our lab, not often, we use an instrument. So I have it here, but it's really instrument based. That you would measure the charge load on that protein, and it's really measuring the net charge. So, and it changes based on the pH of your solution. And we often in the lab, we measure it at pH 7, and sometimes we measure it at pH 3.4. And why we do that? Because let's say we're looking at solubility for acidic beverages and solubility for neutral beverages, and we want to understand the impact of net charge on the solubility behavior of that protein. So we determine at pH 7, is this protein negatively charged? Most proteins are negatively charged because 7 is usually above the isoelectric point of a lot of proteins. So above the isoelectric point, your protein is going to be negatively charged. below the isoelectric point, most of your proteins are going to be positively charged, so you get a net positive charge. The higher the charge, whether negative or positive, that means the protein has more tendency to interact with water because it's more charged. And we're going to learn when we talk about water binding that charged amino acid bind the most with water, followed by polar amino acid, followed by hydrophobic amino acids, also bind water, but to a lower extent. So now the charge is also impacted by salt. Many of you see that your surface charge is lower than expected. And then I tell you, okay, what's your ash content? And then we look at the ash content and say, oh gosh, it's above 5, or it is, well, one protein has 2% ash and the other protein has 5% ash. The one that has 5% ash, your salts in this in the solution interfered with the measurement. That doesn't mean your protein doesn't carry charge. It carries charge, of course it does, but the salt shielded the charge, and it varies from one protein to another in terms of at which salt concentration you get that shielding effect. So when you get that shielding effect, you measure less surface charge because of the salt. Whether the protein is net negatively charged, if you have NaCl, your sodium is going to shield your negative charge, the Na+. And if the protein is positively charged, then the Cl- is going to shield your net positive charge. So when you have salt, in general, you're going to impact the surface charge measurement as well. And that explains sometimes, well, why do we have a higher solubility or lower solubility? And then we try to link not only the surface charge, but we also look at the ash content as well. All right. Questions there? Pre-sulfhydryl group is another assay we can measure. We don't measure it in our lab, but it also gives you an idea, first of all, not just about unfolding, because pre-sulfhydryl groups can tend to be in the interior moiety of the protein. So when the protein are unfolded, you will have more sulfhydryl groups exposed. Also, measurements of pre-sulfhydryl groups is an indication of polymerization as well. So if you have a lot of disulfide linkages via protein molecules, we see a decrease in free sulfhydryl groups. So there are two assays, actually, measurement of total free sulfhydryl groups and also surface sulfhydryl groups. So an increase in surface is an indication of unfolding. A decrease is an indication of polymerization. We don't usually run this test because we can determine unfolding using surface hydro, SDS page, and also the SC measurement. So we don't necessarily do this test very often.
Can you repeat the last thing you said about like more the unfolded proteins, higher is the degree of polymerization, like that?
Oh, no, sorry. Yes, I will repeat. So when oftentimes if you have a free sulfhydryl group in your protein, like beta-lactoglobulin, for example, your SH, that's free sulfhydryl group, is usually hidden inside the moiety of that protein. When the protein denatures unfold, then this will be exposed to the surface. Then you would measure surface sulfhydryl group is a different assay than total. So surface sulfhydryl group is, if it increases, that's because you have unfolding happening. But total sulfhydryl group or total free sulfhydryl group, you can measure that. If it decreases, that means the protein polymerized due to polymerization, forming larger polymers by disulfide linkages. Then the total free sulfhydryl group will be less. Yeah? Okay,
Yeah, thanks.
good. Okay. The last one here, we talked about it with the amine interactions, and this is measuring the either the free amine, well, you measure the free amine in any case. So you can measure the free amine either if you are hydrolyzing your protein and you want to determine degree of hydrolysis, you can measure the free amine, or if you are looking at loss of lysine due to Maillard reaction, then you can also measure the free amine to see if it got reduced, and that's because it got blocked. And then we use OPA reagent because OPA reacts with the primary amine or a free amine that is that has NH2 or NH3 plus that will react with the OPA and gives you a fluorescent or a compound that absorbs lights. Okay. Instrument-based analytical tools, and there are many. So one is looking at changes in structure. A very common one is to look at the denaturation. One, we use differential scanning calorimeter to do a couple of things. First, if we are characterizing a new protein and it's not in its denatured form, we want to know at which temperature the onset of denaturation starts. So for every protein, there is a denaturation temperature, and knowing the denaturation temperature helps us determine best processing conditions to prevent or induce denaturation. Sometimes if I want to make a gel, I really need to induce denaturation to form a thermally induced gel. So sometimes denaturation is needed, sometimes we want to avoid it to avoid polymerization and aggregation. So DSC tells us the denaturation temperature of a particular protein. It also tells us the degree of denaturation. So if we measure the enthalpy, which is the area under the curve of an endothermic peak. So here it is. So this is DSC thermogram, we call it. So you have, you run a program where you increase temperature and you measure the flow of heat. Okay, so when you see an endothermic peak, in this, depending on the DSC type, the endothermic peak is either positive or negative. The DSC we have in the lab shows you a negative peak. But usually we report enthalpy in absolute value because it's basically just the area under the curve, whether the curve is downward or upward, depending on the instrument software. So basically, this tells you the change in heat or in enthalpy that caused a structural change, the uptake of heat, basically. So when you give the protein heat, if you get to its denaturation temperature, the protein is going to uptake that heat and you're causing a thermal denaturation, unfolding of the protein. If the protein is completely denatured, like in this example, soy protein isolate commercial, you will not see an endothermic peak. No matter how you're giving heat flow, there is no uptake of energy because the protein is already denatured. So there's no breakage of intramolecular bonds. That the energy is causing intramolecular bonds to break and for the protein to unfold. So you don't have that. When the protein is its native form, then you will see endothermic peak. So a soy protein that we prepare in the lab, you normally would see two major endothermic peaks for two types of globulin proteins, the beta-conglycinin and glycinin. Glycinin has a higher denaturation temperature because it's stabilized by disulfide linkages, and disulfide linkages add thermal stability to the protein. So it would denature at higher temperature. And then we have an isolated glycinin and an isolated beta-conglycinin. These we isolated from soy flour, and then you will only see one peak designated to that one particular protein fraction that we isolated. So normally in a thermogram, what we are interested in is looking at the denaturation temperature at the peak, the middle of the or the lowest point or the highest point in your endothermic peak. That would be the denatured temperature. Also, there is the onset of denaturation, which is the temperature at which we start seeing uptake of energy. And then the enthalpy, and usually the enthalpy is corrected for the protein concentration. So when we run DSC, we run it at a particular protein concentration, so we can correct for protein concentration, for the protein content.
Pam, why? Okay, so I understand that our native samples that we prepare in lab will have peaks, like they're not denatured. Why are the commercial samples already denatured just from the processing?
Yeah, that's very good point. SPI and specifically soy, they heat the protein during production to inactivate trypsin inhibitor. So it has to be heated to a certain level. Also, there is the defatting step where they use hexane to defat before protein isolation. And in our lab, when we use hexane, we let it air dry. We centrifuge, we throw out the hexane, and then the protein or the flour, we let it air dry under the hood. Well, in industry, they cannot afford to let it air dry overnight. So they do desolvenitization step at high temperature to dissolve, to evaporate the hexane. So that is an exposure to temperature, high temperature. Another place is to get into the spray dryer, you need to have a certain total solids. And oftentimes when you are washing and you dilute your protein, and when you dilute it, if it falls under 15-20%, then they would do an evaporation step, and that's another heat treatment. Another thing that might cause the protein to denature is, in our process in the pilot plant, when there is an overnight, we don't leave it at the isoelectric point. I tell Mitch, reduce it to pH 3. Do not store at the isoelectric point. Whereas in industry, if they have to wait for any reason, they don't necessarily adjust the pH, and the protein will be more susceptible to denaturation. What we try to educate folks in our research is you have to control these steps, or your protein is not only going to be denatured, it's going to polymerize. And that's why most of the protein, pea protein we see in the market is polymerized, has low functionality. Let alone, to start with, pea has low functionality, and then if you abuse it that way, it will even be worse in functionality.
So the commercial soy is already denatured, but it still has really good functionality.
Because soy is different than pea, so it can afford to be denatured and potentially a little bit polymerized, but still have good functionality. Pea, to start with, has poor functionality, and when you abuse it that much, whatever little functionality it has, it loses it.
So
Pam, can I ask a question, Pam?
Yes.
What determines how many peaks are going to be identified on the DSC thermogram?
Absolutely. That's a very good question, Saj. Usually the proteins that are present in the highest abundance will show up on your on your thermogram. So let's say when you run whey protein, although you have albumins, let's say different bovine serum albumin, let's say, but the main proteins in whey, 80% are beta lactoglobulin and alpha lactalbumin. These are the main proteins, so you'll see 2 peaks. And then also glycinin in soy is more abundant than beta-conglycinin, so you see more prominent peak for glycinin than beta-conglycinin. So there is also a concentration effect, although you are putting 20% protein there, but 60 or 70% of that protein is glycine, so you see a bigger peak there. So what you want to know, like you run a gel, you will see which subunits are most dominant, and you would expect, okay, I'm going to see 2 peaks. Mostly it's 2. It's just like most of the main proteins are either 1 or 2. So yeah, good question.
So I have one question.
Yeah.
So when you consider protein concentrate or protein isolate, I think it is not 100% purity. The purity is not 100%.
Yeah.
Probably there may be some fat or lipid, if we say lipid. So in case maybe now you have to use this kind of DSC, how can you distinguish when, if maybe there's a lipid protein complex?
Okay, so that's another good question. What happens here, we don't care about complexes. You will have complex protein starch complex, protein fat complex, and each one of them will have different transition at different temperatures. So there is a transition for fat, there is a transition for starch, and there is a transition temperature for protein. So you'll see them at different temperature zones, the transition of the particular components. And when we prepare our sample for DSC, we usually prepare based on protein concentration, not total solids. So we don't put 20% total solids, we put 20% protein. So depending on how much protein we have in our starting material, we just weigh enough so that we have a solution or a paste that is 20% protein.
Mm-hmm. Okay.
Good. Good. All good questions. Other questions? Okay. So FTIR, we use it mostly to look at secondary structure distribution. Just to remind you, FTIR is a method of a spectroscopy looking at absorption in the IR region, infrared region. And FT stands for Fourier transform IR. And so basically, the bonds absorb light at IR light at different wave numbers, and what changes, what it gets detected is the vibration of the bond once it absorbs the light or the energy. So this is something we cover in depth in undergraduate classes. So I'm not going to go into that principle other than reminding you that this is bending, stretching of bonds, and it's vibrational energy. And it is, all the molecules have bonds, and they're always in movement. They're always moving, they're not static. And when light hits them, and if it's in the range of the allowable transitions, they will absorb light, and then we see, we can detect this absorption of light, and you translate it into structural information. So we utilize this in proteins to look at secondary structures. So, for example, there are different regions in the FTIR for the proteins. The secondary structure region is amide 1 region. That's a very common region that you hear about, amide 1. And it's in between the 1600 to 1700 frequency. And in this region, we have the secondary structure distribution. We have the alpha helix, beta sheet, beta turn, and random coil unordered. So, and in order to determine under amide 1, sometimes you just see it as one peak. And in order to determine the distribution, we say something called deconvolution of the peak. And this is a statistical program that deconvolutes the peaks into those specific regions to give you a percent distribution of the secondary structure. Now, why do we care about secondary structure? Because it tells us a couple of things. First of all, it tells us in a native protein what's the distribution of ordered structure versus unordered structure, like random coil. And also how much beta sheet you have to alpha helix. And the more beta sheet you have, more thermal stability than alpha helix. So it tells us a little bit about that. Also, it tells us in a polymer, if the polymerization happened via hydrogen bonding, if you're forming beta sheet or beta turn. For example, this is important in doughs, in dough system, viscoelastic doughs. Gluten proteins form polymers via beta sheet formation and beta turn formation, whereas like zein, like corn, for example, and weaker proteins like rice and zein that have prolamine, they don't have glutalins, they don't form beta sheets and beta turn in a dough matrix, so they don't have as much of viscoelastic properties. So that is one thing it can be used for. Another is it tells us denaturation at the secondary level. So sometimes protein denatures unfolds, but your secondary structures are not impacted. Sometimes you have denaturation at the secondary level of the protein. So it also, the transitions and the variation between the different distribution will tell you whether denaturation occurred at the secondary level of the protein, secondary structure level of the protein. Here, for example, I show you an example of utilizing FTIR to look at differences in a dough formed with wheat versus a dough formed with intermediate wheatgrass, which is a weaker protein, has higher gliadins or prolamins than glutalins or glutenins. So then hard red wheat. So hard red wheat forms more beta sheet and beta turns than intermediate wheatgrass. So that is one way of looking at the functionality differences between a grain that simulates wheat but doesn't have the same type of proteins than another, than gluten. We also use it, this is an example from Fan, a master's work where she did the cold plasma, and she looked at the changes in the secondary structure of the protein. And for example, let me see if yeah. So here, just looking at the commercial pea protein versus our pea protein that we produce in the lab, you'll see less alpha helix, and you see more random coil than the one we produce in the lab, which has more native structure. So an indication of denaturation at the secondary structure level, you have a lower alpha helix to beta sheet ratio. So if we look at alpha helix to beta sheet ratio, we see a lower ratio for the commercial than the one we prepare in the lab. And if we look at random coil, which is also when you denature the orderly structure, it transforms into a coil-like structure, unordered structure. So we see an increase in random coil. So this is an example of denaturation at the secondary structure level. Any questions before I move on? Raman. So Raman spectroscopy is a very unique and highly sensitive form of IR spectroscopy, and Sears is surface enhanced Raman spectroscopy. So again, from food analysis and your undergraduate classes, you will know that Raman is based on the scattering of light after partial absorption of IR radiation. So when a molecule get hit with IR, it absorbs some of the light and it reflects some of the light that did not get absorbed. So there is a light scattered, but it carries its very unique information about that molecule. And I'm not going to go more into detail. This semester can be spent on understanding Raman, but the idea is that this gives you a fingerprint of the molecular structure and bonds of functional groups in the protein. Now, that's Raman, but surface enhanced Raman, I'll show you how it works. We've done this in whey protein, glycated whey protein, actually. I wanted to understand the impact of glycation on the molecular structure of whey protein. So you have nanoparticles made of silver, and the protein gets fixed on the nanoparticles. And when that happens, you have an enhanced signal, Raman. So when you have an enhanced signal, you get higher sensitivity, you get more structural information. And you can do this in liquid. So IR, usually FTIR, it's better in solids because you have moisture interference. But with sears, you can have, that's the advantage of running sears, is you can have a liquid, protein in liquid, and you can enhance the sensitivity by having it fixated on silver nanoparticles. So you have silver dendrites on a platform, a gold platform, and then you spot your liquid solution, and then you project the radiation, and then you will get the scattering of light, and you get the absorption spectrum. And from there, you would get information as such. So let me tell you a little bit here what we're seeing. So we've done this on whey protein isolate and on partially glycated whey protein. So what we did here is we ran the spectral analysis, and we did PCA, principal component analysis, to determine what caused the most variation in the spectrum. Okay, so if you look at the partially glycated whey protein, you have a unique peak that showed up at 983 wave number. So at 983, we don't see a peak in whey protein isolate, but then we see a peak of a particular intensity in the glycated protein. How is that helpful? It's very helpful because when we look at literature, this is a unique absorption, a spectra, or for a bond between a carbon and a nitrogen. And Maillard reaction is a bond between an amine group and a carbonyl group of a reducing sugar. So that confirmed that you had Maillard-induced glycation occurring, because now it's telling you the vibration of that particular bond, which was really, really unique. And then here we see a shift in SS linkages. So we see a change. So that means we had some disulfide interchange happening. So at a particular wave number, we see an intensity for whey protein isolate, and we don't see it for partially glycated. And then we see different bands that shows that it's present in the glycated sample, it's not present in the non-glycated sample. We see tryptophan and tyrosine shifts, which is an indication of partial unfolding. We see changes in the ionization. So this carboxyl group is not dissociated in the whey protein, but it's completely dissociated in the glycated sample. We see changes in the amide 1 region. We see changes in amide 2 and amide 3. So it really tells us a lot about the functional groups of the protein and how it changed when the protein was glycated. It's very interesting information.
Pam, so theoretically, if you're blending proteins, you could compare, let's say that were your project. So you could compare like the spec of your protein by itself and then blend it and then see how it changes, like how the peaks change after the blend?
Yes, you can look at if there's any changes in the tryptophan tyrosine that indicates unfolding. You can look at any disulfide interchange that could have happened. You can look at changes in the amide region to see if secondary structure distribution has changed. Ionization, yeah, you can get a lot of information. But it won't tell you which protein interacted with which protein, but it will tell you general structural changes. Good. So aggregation, am I getting close to being done here? Right.
Yeah, you have only a few more minutes, like 4 minutes.
Okay. So let's see if I can finish this table. Aggregation, we can look at molecular distribution by size exclusion. We can get accurate molecular weight by moles. I wish we can get moles. It's very expensive though. Multi-angle light scattering detector. It gives you very accurate molecular weight information. But we do have size exclusion, but we use the old UV method of detecting our proteins. So with size exclusion, it gives you the distribution of molecular weight. We can run, let me see if I have, yes. So here we can run size exclusion. And in this case, we also look at molecular weight distribution between the two grains. In this example, hard red wheat and intermediate wheatgrass. So in intermediate wheatgrass, we have lower amount of high molecular weight polymeric protein, which are important for viscoelastic properties. So we are able to fractionate and look at the distribution of high molecular weight polymeric protein, gliadins, albumins, and globulins, and look at differences between these two grains to determine the impact on the viscoelastic properties. So that's one application. Another application here is looking at, again, cold plasma and how that changes the molecular weight distribution. So in here, we run standards and we can determine the molecular weight of our different components. And here in this example, we can see that with cold plasma, we generate large amount of soluble aggregates, and the presence of soluble aggregates usually resulted in enhanced gelation. So we link structure to function. So we look at the commercial pea protein, for example, has low amount of soluble aggregates and hardly any functional proteins, because most of the protein is aggregated and precipitate. When you run on any HPLC, you have to filter your sample. And when you run your sample through filter, all your aggregates are filtered out. So you don't see aggregates in the chromatogram. They will anyway clog your column if you don't filter. So when we did cold plasma, we saw a large amount of soluble aggregates and a little bit of functional proteins in comparison to a commercial pea protein, and it had much higher functionality, especially gelation. We use size exclusion also to look at hydrolysis pattern. So in this example, Chelsea hydrolyzed whey protein using two different enzymes, and we collected the fractions where our hydrolysates are. We took these fractions and we did proteomics on these fractions to look at the characteristics of these peptides to explain, in her case, emulsification capabilities. So this is a table she generated from her chromatograms where she looked at the different whey protein components. Beta-lactoglobulin usually at pH 7 migrates as a dimer, and then alpha-lactalbumin migrates as a monomer, and then the generation of peptides here. And depending on the enzyme we use, trypsin versus a different enzyme, we can see what gets completely hydrolyzed So trypsin has high affinity to beta-lactoglobulin, for example. So we are able to determine that with running size exclusion. So looking at enzyme specificity, collecting our hydrolysates for further analyses. MALDI, okay, so I think my time is up. So I don't want to rush through that. I will record my lecture and explain that more slowly. Yes? Any questions? No questions? I thought I heard somebody. Were you just telling me time, Brittany?
Yeah, it was just me.
Yeah, you're telling me time. Okay. Yes. So, of course, every time I teach this class, I add more information and time runs by. But all good information. If it's okay if we don't finish all of what I have planned for the semester, but it's all good information. I'll keep the slow pace. Am I going fast for you still, or do you feel that the pace is good? You can give me feedback.
I feel like the pace is fine. We just have so many questions.
That's good. You know, you always can interrupt me. I'm sorry that you won't be able to interrupt me when I record, but that's why it's important to come to the following lecture with questions. Okay? The more questions you ask, the better you're going to get the material. And it's okay if we don't get everything finished before the exam. Yes, you will have less material to study. Now, don't come with 100 questions just to delay me, but okay, you guys, I'm gonna say good night. It's midnight almost here.
Oh.
Bye, Pam. Thank you.
All right, bye-bye.
Good night.
Bye.
Bye.
Bye, thank you.